in the kernel driver LAN. So first topic is box crashing. The DRM 950 driver kind of has a reputation of being the most regretting thing in the kernel, and we, historically at least, got pretty much every month a nice beat up from Wes Torvalds and all the guys. Past year we fixed a lot of bugs. I think at the beginning of 2012 there was like something between 500 and 600 open bugs on free desktop and kernel.org/source. And we're now down to something between 100 150 open bugs. We did not just close these because yeah, we actually, I think in the beginning of 2012 there was like months where we fixed around 100 to 50 to 100 bugs per month, and did insane things like that. And especially regressions. I think back then we had like something between 100 and 150 open kernel regressions, well, the reported ones, and now we're down to much more reasonable, I think 20, of which like half of them are stuff that QA just reported or recently reported. So we do break a lot of stuff, but that's kind of because we actually do a lot of stuff in general. One thing that helped greatly with improving quality is actually having a test suite. I mean, 1.5 years ago we had like 0 automated kernel testing. And we kind of started with just using the Intel GPU basic tools, and it's amazing how bad the test suite you can put together and it's still useful to catch the bug. It's pretty good nowadays. We actually implemented some debug-fs knobs and tricks and things to exercise corner conditions like GPU hangs. We have test cases for GPU hangs so that the kernel doesn't deadlock when a GPU hang happens, and we do simulate them by turning on some debug-fs knobs. Just recently there was in kernel 3.7 there was a regression around with a fun interaction between the shrinker callbacks on the memory pressure and our relocation slow path, and we added to exercise these code paths, we added special knobs to drop all the caches and memory mapping so that we can force these code paths. We probably need to add one to disable all the pre-faulting so that we actually hit the slow paths reliably. Originally we started with the automated test runner just because that was like 5 minutes of works, and now it's integrated in Piglet, so it's still in the Intel GPU tools repository, but we can use Piglet to run tests, to filter tests, and to display the nice regression results. Future about kernel tests is we have fairly nice coverage for the gem part of the kernel, the actual command submission stuff, with lots of corner cases and historical buggy parts covered. Mode setting part is pretty much not covered. Like, we have some fairly basic stuff. The last few weeks and months we worked a lot on testing page flipping. It turns out to be totally broken if you actually be paranoid about your timestamps and stuff. The other thing,
No one actually cares.
no one also cares about like the VBlank counter. It goes back and forth. It's bad. The other big area is GPU hangs. Billy discovered in his atomic page flip stuff that if you schedule a page flip and the GPU dies, the kernel just falls over. So don't page flip. we need to fix that for you. Anyway, so that's probably the other big area, kind of the corner cases, exercising more corner cases in the GPU hang code, because that just has to be. Well, one thing actually, which I'd like to see a bit of interest in is kernel tests across different GPU drivers, because every time I kind of look through the different drivers to reverse and core DRM stuff, I noticed that every driver kind of implements the corner cases slightly differently. So we have a common IOPTL interface, but not a common ABI. So maybe that could be something for like Wayland or the KMS talk to actually test that stuff. While we're talking about bug reports, there's kind of pet peeve of mine, and it is a strange request because I think pretty much every other open source project asks you not to do that. Anyway, it is. Dear GFX bug reporters, please file duplicates. I mean, essentially in the kernel driver we have two bugs. One is I have a black screen, and the other one is I have a GPU hang. That's the only two bugs we get. Usually only once we have the bug fixed, we can actually know whether it's a duplicate or whether it's a different thing. So if you have a GPU hang or a black screen and it's kind of not clear what, please do not add your logs and things to another bug report, because that's going to go messy real quickly. We really encourage bug reporters, please file duplicates. It's much easier to kind of mark a bug as a duplicate, we do that all the time anyway, that we try to untangle like 5 bug reports spanning 3 different generations and totally, completely different hardware, like, dude, you do not have the same bug. So, yeah, that would be nice. The other thing is, if you have a bug, please do not write an email just to your kernel maintainer because he's a lazy bastard, I know that. Next topic is passable display enabling. One thing in Haswell which is different is LVDS connector output support is gone. For panels, it's all going to be EDP. SDVU, adding connector and coder support is also going. And the VGA output is pretty marginalized. It seems to be dying, which I kind of like. And the other thing is the output ports moved around a little bit. So maybe let's look at how things have been since Iron Lake, Sandy Bridge, Ivy Bridge, all the Intel HD graphics chips as marketing system. We essentially have the CPU, on the CPU, the graphics for it, with 2 output pipes, or actually 3 on Ivy Bridge. Then all the outputs are actually on the PCH, so there we have display ports, SDVO, HDMI, and all that stuff. We have a big MUX there, and we have 2 or 3 FDI lanes which are moving pixels between the 2 chips. And there's kind of the special case of EDP there for panel displays. Now, if you look at what Haswell all kicks out, there's kind of not much left. There's VGA left, there's DisplayPort left, and HDMI. Now the thing to know is an FDI link is actually just a DisplayPort link on a motherboard. So in a way we already have DisplayPort on the CPU, and the trick that the hardware engineers now pulled off, they improved the FDI ports a little bit so that the FDI ports can now also output HDMI signals, and then essentially everything on the PCH is gone besides the VGA port, and they renamed things from FDI to DDI. So we now have a bunch of DDI ports on the CPU die, 1 FDI link, and 2 the VGA port. That's kind of the really big rework on the display side for the kernel. One of these major changes that only happen once every few years. We had to re-architect our code quite a bit. One thing you notice, on the old design we had multiple FDR links, so we picked the FDR link corresponding to the pipe. Now we only have 1, so we had to rework all the code that dealt with the PCH and FDR links to be able to specify the FDI and PCH pipe independently of the CPU pipe so that we could reuse all that code. The DDR links are working quite differently. One thing now is the DDIs are kind of like the old EDP port, and those had a nice problem. There was a decent chance to get a black screen bug. The reason for that was that our code actually had like the wrong enable and disable sequence. We had a few hacks on the enable side, but on the disable side, you need to disable ED or CPU display ports the other way around. Like first you need to disable the pipe and then the display port. Whereas usually it's like you start at the outside with disabling until you reach the pipe. So that could cause black screens. Also on like all the machines with the EDP port, like this one was actually buggy when I bought it, which is not too nice. So the reason for that problem is that half a year ago we still used the common DRM CRTC helpers to drive the mode set sequence. And in one way they were kind of too flexible, as in you can enable and disable encoders and CRTCs completely independently, which doesn't work on DisplayPort. If you, especially on the CPU DisplayPort and DDI ports, if you do things the wrong way around, it just falls over. So you can't actually independently disable and enable things. So in that regard, it was too flexible. The other thing is it was not flexible enough. It could actually not map the order of enabling and disabling things on the Intel hardware to the CRTC helpers. It just didn't match. So the thing the code did was it moved part of the encoder stuff to different enable. Part of the encoder enabling was actually in the encoder mode set, which should not enable anything, but we have to move it ahead. And part of the disabling ended up somewhere else, and we had a lot of checks to see what the actual hardware state was, because the CRTC helpers could enable and disable things pretty freely. So the thing we've done is to completely rewrite all that stuff and create a set of helper functions specifically for the Intel driver, so that we could drive the mode set sequence the way we actually want or need to do it. There's kind of two ports. One slightly orthogonal is DPMS. Originally, the DRM DPMS IOCL supported like 4 states, on, off, and a bunch of standby and sleep modes. Current hardware does not support that at all. There's either the thing is running or it's not running. The bad thing was kind of the code had to be pretty pessimistic. So because some old platforms actually supported the in-between state, we had to keep the CRTCs running all the time in standby and sleep modes, because the CRTC helpers were too flexible and didn't actually tell us what we needed. So one point of the rework was to clean that up and drive the DPMS purely from the connectors. So the connectors gets the DPMS request from user spice, decides what state it actually wants, and then tells the entire display pipeline, okay, I have this state, please make it happen, instead of everything being independent of each other. The other thing is the mode set sequence is now completely driven by the CRTC. So the CRTC decides what to enable and in which order, and we only ever enable everything or nothing. So there's no longer that kind of freedom where you can just enable, disable specific encoders. In the code itself, we implemented some new tools and infrastructure. 2 things are kind of important. One is output staging. The problem, and I know the problem with the CRTC helper is that while doing the mode set, it overwrote the old software tracking state with the one we wanted. But while disabling things, we need to know what the current hardware state is, so that we can disable things in the right order and correctly tear down everything. But the CRTC helpers already overwrote all that information, so we have to actually like check the hardware state, which is kind of crazy. So the new code does the new output configuration in a staged area, so that we can disable everything with all the current information still in the software, which nicely streamlines the code and removes tons of stupid what is the actual hardware state kind of checks. And only once we have disabled everything and start to set up the new configuration, we commit that output state from the staging area to the real pointers and data structures, and then enable everything and do the mode set sequence. The other thing is we added functions to, or kind of real infrastructure to read out the current hardware state, which has kind of two purposes. One is if we try to do the correct mode set sequence, that's all nice and dandy, safe for when we boot up, then we have some unknown state by the left behind by the BIOS. And if we just disable things in a random order, we will end up with a black screen, which is not nice. So the first requirement for the hardware state readout code was to be able to read the and map the BIOS state so that we could correctly disable the BIOS state and not break the hardware. And the nice benefit is that we can use these functions to check software and hardware state, cross-check them. So after each mode set, we run through all these get hardware state functions and check whether the reality actually matches up with our idea of what it should be, which helped a lot in fixing bugs and preventing regressions, because yeah, we had to pretty much rewrite the entire infrastructure, and I'd say thanks to the hardware state stuff, that worked out pretty well. We had like, I think 2-3 regression records for 80 type series. So results is the paranoid set state checker is like awesome, and we plan to roll that out on even more parts of the hardware state. Currently it's mostly concerned about the output routing, like from the pipe to which connector and that kind of stuff. I think we need to put more such infrastructure in place for the CRTC, for the pipe configuration itself, like the clocks and the bit depth and stuff like that. The other thing is all that flexibility in the CRTC helper essentially has blown up the state space massively, and by cutting it down to just one single boolean essentially, is the pipe enabled or not in that configuration, and there's not like in between stage, we could massively simplify the code. It did enable us to actually implement Haskell display port support. That's the reason why Haskell display port support only works in 3.8, because we had to first get the mode set infrastructure in shape. It just did not work on the old CRTC helpers. One outcome is also, up to this rework, all the DRM drivers kind of used the same CRTC helpers. So it wasn't clear whether these helpers are really helper library functions the drivers could opt out of it, or whether they kind of slowly morphed into being part of the DRM driver interface. And I can say it's looking pretty good. Like, you can actually write a completely different mode set infrastructure and it all still fits. There were a few ugly corners in the FBDEF emulation code, but I just last week submitted patches to fix that up. So you can implement your own CRTC mode set infrastructure, still use the FBDEF emulation, and still use the output probing helper functions. It's still all works. So looking ahead for mode set stuff, there's a bit less atomic stuff on the table, certainly, and especially for some of the resource sharing issues. I think having our own mode set infrastructure will help greatly, so that we can pass around special properties and implement resource constraints. Like, for example, on Ivy Bridge we have 3 output pipes, but in a lot of the resources are actually, we only actually have like 2. So if you want to use more than 2 PCH ports, you need to share the PLLs. There are link bandwidth constraints on pipe B and C. So if you use both of them, the link bandwidth cannot go above certain limits. Whereas if you just use one of them. The other thing which we're kind of working on is fast boot support. With all the getting the hardware state readout code, we actually have a pretty nice idea of what the current BIOS or the state is that the BIOS set up for us. So if we improve that a little bit, we could just take that mode set and not change anything and just keep on booting, which shaves off a mode set sequence from the boot sequence, so it saves about 1-2 seconds of boot time if the DRM 15 is actually the limiting part of the boot sequence. So the idea there is that the firmware does one mode set at boot to set up the hardware. We read out the entire state and just flip over to the kernel frame buffer, and X or Valent or Surface Flinger does the exact same thing. So you have no flicker, no nothing, and only one mode set sequence in the entire boot. That's kind of in the works. Some minor stuff we did last year, well, minor, is edit improvements. I think at the beginning of last year, it could easily happen that reading an edit would like take 1-2 seconds. And some distros were famous for doing that every 30 seconds in a background task. So every 30 seconds, your mouse cursor in Windows system would like freeze for 2 seconds, and then you would go on again. Awesome. So we massively improved the throughput of the edit reading code, and there's still some issues with caching, like on some configurations where we could do better, but generally it's much faster. And the other thing, which is still an ongoing mess, is block support. The code was kind of ugly and complicated and not really clear, and the other problem is that there seems to be an awful lot of hardware out there where the hot block lines are kind of wired too near the charging circuits. So if you plug in your laptop into main circuits to charge your batteries, you get like 10K interrupts per second on the hot block pin, which does kind of affect performance. So we're working on that one. It's kind of also related, because if hot block support is not reliable, we cannot really cache the edit that well. So I think we first need to get the hot block into better shape and then move on. One thing for the edit improvement was that even with all these speed ups, reading the edit over I2C just takes like 25 milliseconds. And that means we will drop 1 frame if this is a blocking operation. And up to 2 weeks ago, that was the case, because there's just, in the kernel there was just one lock covering the entire mode set subsystem. So if something has been was reading the edit in the background, that meant that you could not page flip or move the cursor. And that's now fixed with the reworked mode set logging, which is merged. Oh, there's a little bit of 2 letters missing. Which was just merged for 3.9 into DRM next. And we switched over to P per CRTC locks. So now you can page flip on each CRTC independently and also move the cursor around, while other stuff is going on in the background. So the output pulling or edit reading stuff can happen in the background while you still page flip. And that was actually the simple part of the rework. The much more invasive part, kind of covering all drivers, was to make finer grained locking possible. We had to implement real lifetime management for frame buffer objects in the kernel with reference counting. Because previously, as long as you held onto that global mode set lock, it was guaranteed that the frame buffer would not disappear. And now, with just CRTC locks, that guarantee doesn't hold anymore. So we had to rework all the KMS IOCs to do proper reference counting, which obviously covered all the drivers. So that's essentially what's been going on the mode set side. So let's look a little bit at gem, what would happen in gem landing, submitting command buffers and work to the GPU. Overall, it's lots and lots of little bits of tuning here and there. I'll cover some of them later on. One kind of user space visible feature was hardware context support, which means the hardware has some infrastructure to save and restore a bunch of registers with the GL state, and we need that to implement stream-out support when there's a geometry shader in the pipeline, because then the Mesa driver can pre-compute how many vertices the geometry stage will spit out through the stream-out support. So we need to save and restore that, and that's the way the hardware is supporting that. So that's been implemented. The other big thing is cacheability control. On Sandy Bridge and Ivy Bridge, we have this very nice, very large shared cache between CPUs and GPUs. And that essentially may speed up transfers between CPU and GPU massively. It's all nicely coherent now. On all the chips, GPU and CPU are not in the same coherency domain, so the GPU just directly writes to main memory. And if you want to read back something, you just first have to flush the CPU caches and then read it back from main memory to not read some stale data from CPU caches. Same for writing. If you write something on the CPU side, you afterwards have to flush out the caches so that the GPU can actually read it, because the GPU does not read CPU caches. And that's all pretty slow. On the upload side, like moving data from the CPU to the GPU, we can use write combining mappings, which are pretty fast, which essentially run at main memory bandwidth. But for read back, there's nothing the CPU can do, which is reasonably fast. But all the Intel GPUs implement some support, even the really old ones, to use the Blitter engine to move from the GPU uncached domain data to the CPU cached domain. The cacheability control support that we added recently exposes that to user space. So now user space can create cacheable or snoopable buffer objects as kind of staging areas, render something on the GPU, blit it to the cacheable thing, and do some software fallback rendering at full speed with the CPU in the cacheable area, then blit it back to the GPU domain and do some hardware blending there again. And Chris Wilson uses that to great effect in SNA. It's essentially one of the reasons why SNA exists, or cacheability control exists because of SNA. So that's kind of the two user space visible features. The big thing internally to GEM is the removal of the flushing list. For context, GEM kind of started out with the idea that it is beneficial, or it kind of sounds beneficial, to keep track of which objects are in which GPU caches. Like this texture here is currently in the read domain for the texture sampler caches, so we do not need to flush the texture caches when we want to read something from that. But that's kind of, the idea was like, if you do render to texture and stuff like that, that you only flush the render cache and the texture caches and the different things if you actually have to. The problem with that is it's really complex. There have been a lot of bugs in that code where we kind of lost track of a few things, and it was completely unnecessary because due to workarounds, we flush all the caches on each batch buffer anyway. So all that careful domain tracking and cache tracking was totally for naught. Even those, we tried to really, really optimize and batch up render cache flushes. So if there was a dirty object around, we put that on a flushing list, and only later on when the kernel thought, okay, I'm going to flush this cache out, we moved it out of it again. The thing was, due to workarounds and all that thing, the cache was flushed already, but the kernel still had the object on the flushing list, then emitted the flush, moved it to the active queue again, which means it actually caused stalls and additional delays because every kind of render operation caused the object to get moved ahead of the queue again if you want to read back things. So we ripped that all out completely. Kind of the reason why it stuck around for so long was that on Sandy Bridge there was a bug in the cache flush implementation. We actually relied often calling the cache flushing twice. It didn't work the first time around. There was a sync point missing in it. So that's the reason why we didn't take this out like 2 years ago, because we had a bug in Sandy Bridge. But that's now fixed. All the flushing list is gone, all the complexity is gone. What we still have is the GPU domains, but we're probably going to rip that out there in the future because we don't care anymore. The only thing we care about now is the thing in the CPU caches, or so that we need to flush the CPU caches, or is it already coherent for the GPU? And nothing else matters. So that was a great simplification of the jam code, and yeah, it's nice to kind of remove that source of bugs. For tuning, 3.7 merged the on-back tracking code from Chris, which resulted in some nice regression disasters. That's the bug with the strange interaction between the OOM shrinker callbacks and the slow path of the relocation code. The on-band tracking is kind of, previously when we removed an object from the graphics address space, we also put it back into the CPU domain. So if you moved something around because you had to make space or reorder objects to, how you say, so defragment the address space, we flush the caches for each of these objects again. So it was really wasteful. And the on-band tracking essentially just keeps a list of objects around which are not bound to the GPU address space, but which are still cache flushed and so convenient for the GPU. And one of the results or the effects of that work was that the DRM 950 driver is now really keen on sitting on a few gigabytes of main memory, like on everything if you wanted to, because we cache everything really aggressively. We keep onto massive amounts of buffer objects, and now with the on-band tracking we can keep onto everything of main memory essentially. So we did hit the shrinker callbacks much more often, which exposed a pretty old bug in the relocation code, in the slow path of the relocation code. And the slow path of the relocation code is kind of only likely to hit when you're having memory pressure. So we kind of had a perfect storm there, but it's fixed now. The other thing is we did a lot of small bits and pieces to reduce the so-called mappable pressure. We have at least if you ignore Ivy Bridge, we have just one GPU address space. We can't do per process address spaces. We haven't even implemented it on Ivy Bridge yet. And there's one part of that address space which is usually much, much smaller than the entire 2 gigabyte thing, which can be accessed from the CPU. And a few things like using the GPU detailing support for uploading textures, and a few other things kind of need to access a buffer object through the mappable space. So there's quite a bit of pressure, or increased pressure, on that portion of the GPU address space. And a lot of the things we've done last year were implement tricks and clever optimizations to use that mappable space more efficiently, and also to not use it if we don't actually require it, so that we don't have to move objects in and out of that special section of the address space anymore. The third thing, which was just merged 2 weeks ago, I think, for 3.9, is the no relocation over a fast path optimization. Because the kernel is free to move around objects at will, user space needs to pass in a giant list of it put pointers into its command submission to the respective texture objects, random objects. And if anything moved around, the kernel needs to go through that list. Well, it always has to go through that list, checking whether anything has moved around and fixing up these pointers in the GPU commands. And usually, with all our hard work to try not to move things around, like reducing mappable pressure, in most cases there's no fix-up required. But the current interface forces the kernel to go through the entire list. So we slightly changed the guarantees that user space needs to guarantee the interface semantics, so that user space can do a few funny things that no one really needs anyway. And now the kernel can check at the beginning of the exec, well, for command submission, whether anything moved. And if nothing has moved, it does not even look at the relocation list. And on a lot of benchmarks, that's a few percent. It's kind of tiny stuff. The gem future, maybe we will get around to real per process address spaces. It's kind of been on the to-do list since 1-2 years. And yeah, this kind of links in with the next talk. The main reason for that is better insulation between processes, just kind of security, so that you can't read what the other guy is rendering, which would be nice. Another thing which has been on the table since, I think, even longer, is user pointer support to slurp in arbitrary amounts of mallet memory and use that directly in the GPU. Chris Wilson has kind of proof of concept patch used by SNA since forever, mostly because X sucks and there's no way to give X a special shared memory blob that could be used by the GPU, so you have to take the shared memory from X and use that, the user pointer, to slurp it into GPU for uploads. The other thing is, with the online tracking list, we're pushing the VM much harder, and currently in GEM we have like one lock to rule them all and protect everything. And the problem with that is, if you're holding that lock and you're sitting on a few gigabytes of main memory and you're trying to allocate even more to submit the command, the kernel has kind of hard time getting onto more memory, because you're the guy holding onto everything, and you're also holding the lock that you need to grab to free some of that memory. So our code is littered with special cases to handle that ourselves. So every time we have an allocation failure, we fall back to slow path, kick out a bunch of our own objects and try again. and we have some pretty horrible tricks to make that work in a few more cases. The problem is that works pretty well. We have some rather harsh and paranoid tests in Intel GPU tools to stress the VM. That works pretty well if the only high memory usage thing is the GPU. As soon as you have something else like which pins a lot of memory or uses a lot of memory, like a second GPU, it will totally fall over. So one of the things which is probably on the table is to switch to more fine-grained locking, which essentially means per object locking, so that exec buff could hang onto a bunch of objects, but the shrinker callback could free a bunch of other idle objects, so that we don't have these OOM issues anymore. The other reason for switch or looking at the per object locking is kind of the last topic of the talk is DMA buff fences reservation stuff from Martin Longhorst and Rockcroft, these two guys over there. That's the thing is essentially TTM trimmed down. So yeah, I lost. And currently it's just used for synchronization between multiple GPUs. So Martin Longhorst can actually render on a Radeon GPU, display on an Intel GPU without tiering and without the CPU doing much at all. It all works kind of behind the back. The cool thing with Martin's patches really is that he added lockdap support, which I think is a complete requirement. We have around the FBCon a bunch of deadlocks recently. Maybe you've seen the discussions. And we only discovered these deadlocks because I added lockdap annotations to the console lock, which is kind of a special type of lock. And previously we just had a constant background noise of Mozilla reports in distros that, well, my machine sometimes dies and I get a black screen when booting. So in graphics we have a lot of interactions with different subsystems, especially if there are multiple GPUs involved. So lockdap support to get reports of deadlocks before they happen is really important. Figured I might cover a few of the opens before we converge that some of the core kernel guys need to review the mutex changes. Another open point is what are we going to do with Android? I mean, the cool thing with DMA buff is we now have DMA buff on the desktop used for prime, buffer sharing, and DMA buff used as an interface to iron. So across SoCs and desktop, we have the same interface in the kernel used to share buffers, which is pretty nice. For synchronization, Android has a completely different thing. Yeah, we kind of need to figure out what we're going to do with that. Because it would be nice to have something unified, so that driver writers do not need to implement the same concept twice. If we go to fences and synchronization, integration with i950 gem will be fun, because we need to switch the entire locking scheme to per object locking. I do not have a plan yet for that. So I guess that will be something interesting to do this year. And yeah, like I said, if we have per object locking, which the DMA buff fences require, we should also be able to do much better out of memory handling and not just follow if anyone else, but the DRM i950 wants to have a few kilobytes in memory. So that's been it. Summary of what has happened, what's going on. Much fewer bugs, please report them still, and do file duplicates. And we have much better QA tooling, actual kernel tests. We have pretty nicely improved mode set infrastructure, which should enable us to do a bunch of cool things in this year, like atomic mode set and FOSDEM. We have a nicely tuned gem, which probably edged a few percent here and there out. And in the case of the cacheability control, actually, made read back so much faster. Like it's totally impossible to. You can actually use efficiently both CPU and GPU for rendering, and they can collaborate with those all out. And for GEM, actually, the big thing is the changes I anticipate around DMA buff because of the locking changes. I guess that will be very invasive and tons of fun to integrate. One last thing, maybe you heard, they're hiring. So if anyone's interested. Anyway, questions?
No, not just a question, but if you're a kernel guy, please review the mute exchanges. I don't think Daniel Vedder is trusted enough, so we can finally get the code in and get it used everywhere.
Yeah, I guess we need to harass a few of these guys.
So if you know a kernel guy or are a kernel guy, please do so.
Yeah.
So for the QA tools, how portable are they to other operating systems? If they provide the an XOR KMS compatible driver interface.
What currently, I mean, most of the kernel tests are around GEM currently, so it only exercises the Intel GEM interface,
Okay.
which is specific to Intel. I mean, all the command submission are kind of for each driver has their own.
Sure, but like for example, I mean for example, like for FreeBSD or OpenBSD, as opposed to for ATI or.
Well, actually, we do get patches every time I shell out a release. I get patches from Alan Cooper-Smith to make it portable to Solaris. So people, and yeah, there's some other people who port it to kind of other systems. I mean, Android is kind of a different system.
Yeah.
If you just look at user space, I think there's some other stuff going on where people use our driver as a basis or implement something compatible to our driver and yeah, use the test. I'm not sure whether anyone actually runs the kernel tests outside of Intel much at all. I think Adam Jackson for Red Hat recently tried to run them on his latest Red Hat Enterprise Linux backports and noticed that his kernel oops is because he doesn't have all the backports and bug fixes. So I'm not sure whether too many people actually run it. And usually it's the case, if you do not have the latest upstream kernel, it's going to kill it. Because there's so many, yeah, and the exercise all the common cases. So, yeah.
How much involvement do you see in open source driver development from the side of Intel? Do they increase their?
Intel? You mean involvement from Intel in open source drivers?
Yes.
Well, I think if you look at DRM changelogs, we do more than 50% of everything. I don't know the NASA numbers, but Intel is pushing a lot. And if you look at team sizes for the kernel, we had 2 years ago maybe 2.5 kernel guys. If you kind of look at what people are, what are the jobs and things people do, and now we have like 12 guys working on the kernel. You do not see a lot of that stuff because it's kind of internal mailing thing which you're not allowed to publish yet and talk about. But Intel does push a lot of upstream. I mean, yeah, Intel OTC is upstream first. Yeah.
I was a little bit late, so maybe I missed it. But do you know how many people Intel employs altogether working on the kernel on Mesa in the graphics, on the graphics stuff?
I don't know.
So there's
On the driver?
9 people who work on Mesa full time.
Thanks.
Yeah. Yeah, I think around 12 on the kernel. The thing is, a lot of I mean, it's not just Intel people at Intel OTC, but there's product groups who use our driver to do something, maybe add some additional magic on top. And so it's kind of hard to, if you look at, look just at the core driver developers, there's maybe about around 30, 20, 30.
It's a pretty good number, and we're still hiring.
Yeah.
So
Yeah.
my 2 cents on the Intel driver, so I did some performance testing for mine, and the Intel Visa driver outperforms the Windows driver handily, so at least in my testing.
Yeah, we do beat Windows sometimes.
So the driver is quite impressive. Well, it crashes on my computer when I run it. The things that work pretty well, and I think that's the crash is an isolated problem and not a structural deficiency.
Yeah, the thing is, a year ago we did not really have working relationships with the hardware guys that were well, so we've been out of the loop with respect to workarounds on that's also a thing we improved internally a lot, so we implement most, at least for newer things. That's kind of the problem with hardware guys, they're like 3 generations ahead of everything that ships. So if you're coming around with the Sandy Bridge, which is like last year's product, it's like, dude, I've not worked on this in years. So yeah, we'll be catching up there, and we have better process in place to not like miss the basics there. And yeah, things seems to, there's still GPU hangs. I mean, like I said, it's black screens and GPU hangs.
Yeah, black screen SSH is working.
Any other questions? I guess otherwise, okay. Thanks for listening.